Not. There we go. Dodged a bullet. First of all, let's take a look at this and see what type of compound are we trying to make here. You guys tell me, what are we trying to make here? Well, what's the notable functional group that you see? What's the notable bond? You guys are trying to make me feel real awkward here. What's that? An imine, yeah. You have a carbon-nitrogen double bond, right? So you know you're trying to form an imine, okay? Now, what materials do you need for an imine? You need two basic things. What are they? What's that? Nitrogen from what type of compound? There's a few different things that contain nitrogen. What's that? I thought I heard somebody say something. Where does the nitrogen come from? NH2, yeah. NH2 by itself or with something attached to it? NH2 minus, and then let me rephrase it. NH2 minus is a base, it's called the imide ion, or like an R group that has an NH2. So yeah, a primary amine, right? So you know you're going to need a primary amine eventually to make this, and what is the primary amine going to need to react with? Mild acid, yeah. What else? What's the other carbon-containing part? An aldehyde or ketone, okay? So that tells us something here, right? That tells us that we need an aldehyde or ketone plus a primary amine, right? So if I'm looking at this one, right? I'm kind of looking at this as the dividing line, right? We said whenever you're trying to predict the imine product, basically what you do is you replace the oxygen in your carbonyl group with the nitrogen group, right? So probably stands to reason that if our carbon-oxygen double bond was over here, right? Then we could get our imine by adding that primary amine. Okay, so that's kind of the approach I take here. Look to see what type of material I have at the end. It's an imine, it's one we've made in this chapter, right? Figure out what the parts are. So now all we have to do is we have to figure out how to get from benzene to the aldehyde. And that's going to require old chemistry. Right? How many carbons are we trying to get on the ring here? saw a couple of people flash their fingers. Can you tell me in words? Use your words. That's what I used to tell my kid when she was a toddler. Actually, I don't think two. How many? Can we get? Yeah, this is just one. Yeah, we're just trying to get one of them on there, right? All right, so how do we get one carbon onto a benzene ring? This will be on your exam. How do we get anything on a benzene ring? We have to use electrophilic aromatic substitution, right? Which one of those will get us carbon? Friedel-Crafts alkylation, yeah. Right? Remember, if we do Friedel-Crafts alkylation with an excess of benzene, that will allow us to put methyl group. So now we need to get from the methyl group to the aldehyde. By my best guesstimations, it'll take about 3 steps. Yeah. Now we can work forward from toluene, or we could work backwards from this, either way. Which way do you guys want to try? Forward or back? Come on, give me some interaction. No, I'll go backward. All right, so what's one way to make an aldehyde? There's a few different ways. What's that? ECC. What would we add PCC to in order to get an aldehyde? Primary alcohol. Yeah. Yeah, so if we can get an OH group on that carbon, oxidize it with a mild oxidizing agent, then yeah, that'll get us an aldehyde for sure. Now we just got to figure out how to get an OH group on there. We can't do it directly. You can't just stick an OH group on to a CH3. But you can get one on there pretty easily by replacing something else. What would be the missing reagent in here? What could OH replace in order to give you that blessing? Or if you want to think about it from this point, you could say, well, I know I need to modify this alkane group here. What can you do with an alkane group? What can you do with a CH3? There's not many options for that. In fact, there's really only one. You can do a chlorination of it. Absolutely. Radical chlorination. That would work. And you see now you have a leaving group on there. You have a CO. And once you have that, then you can fill in this blank over here, just an SN2 reaction. Okay? Does that make sense? How we did that? All right, let me take a little moment here. I just want to sort of try to spur you guys on a little bit. I noticed lately you guys have been extra shy about answering this, except for like maybe a couple of specific people. The reason I ask a lot of questions is because, number one, I want you to keep engaged. I don't want you to just be passive and listening to me. It makes you think more if you're actively trying to come up with answers here. And number two, I mean, I think if you guys are willing to offer answers, even when they're wrong, that can oftentimes spur a lot of discussion, a lot of good discussion on why something's wrong, even if it's logically mentioned. I know it's difficult sometimes to volunteer answers, but I know some of you guys have them because I'll see you sitting there just sort of waiting. Either you're not bothering to look them up or you've already looked them up, answered them in your head. I used to, my first couple of years of teaching, I literally would just go down rows, call people individually for specific questions. I stopped doing that because it seemed, I felt like I was kind of putting people on the spot a little bit, and I didn't want people to feel too nervous about answering. But, you know, it's something I wouldn't rule out pulling out of my pocket if I have to get you involved. Right? So please interact. It really helps the class move along. You guys are a lot more interesting than I am. All right. Are there any questions about how we got this one? All right, let's try another one. All right, let me see. All right, this is a pretty good one. All right. So there I've got a setup. I'm trying to make an alkene, but I have a little caveat here. I want this to be the only possible alkene product that you can get. So I want very, very specifically just to get that guy right there. All right, so we talked about a few different ways of making alkenes throughout the course of the year, right? Do we know any that are very specific, any techniques that are very, very specific for putting the alkene group in a particular spot? Wittig reaction, yeah. Wittig reaction allows us to put an alkene group at a very specific spot. So if I'm looking at this, I'm probably thinking, okay, I'm going to do a Wittig reaction. All right, that's going to be towards the tail end of this. All right. Now, for a Wittig reaction, number one, we need a Wittig reagent. And number two, what else do we need?
Aldehyde or ketone?
An aldehyde or ketone, yeah. Right. Guess how you figure out where the two fragments are? Take your double bond, snip, 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 right over there. Okay. So if you're looking at this, over here, you actually could do this two different ways. There's more than one route here. You could actually make either one of these the aldehyde or ketone, and either one of those the Wittig reagent. I'm going to choose to do this one as the aldehyde ketone. All right, so your Wittig reagent then is going to look like that. And remember, with this one, you have the funny little box intermediate. The negative carbon attacks the carbonyl carbon. The phosphorus attacks the oxygen, makes the box, which then rearranges to give you your type. Okay. Does that make sense? Does that ring a bell? Any questions about how we came up with that? Right. Now, for synthetic purposes, given the guidelines I gave you, really now all we have to do is figure out how to get from there to there, and also briefly explain how we made the Wittig reagent. Now, getting from here to here, that should be really easy, considering we just did it.
Same thing.
Same thing, yeah. Well, almost the same thing. Actually, no, yeah, you would do the same thing. You definitely would want to do a chlorination, because if you did a bromination, it would be selective and only go there. So you chlorinate that carbon. Replace it with an OH. And then add some PCC. So then we would need to also describe how we made our Wittig reagent, because remember, we have to make that fresh every time. Right? So what do you need to make a Wittig reagent?
Alkyl halide.
Need an alkyl halide, right? So I'll sort of make it in this little box over here. It stands to reason that the halide, the halogen, is going to be at the point of attachment. What else do you need? What does the alkyl halide react with? Triphenylphosphine, which is this, right? That puts a positive charge on your phosphorus. One more thing we got to do, we got to get that negative charge on this carbon, right? To do that, we added a very particular type of base. What was it? Butyllithium. Very good. There we go. And boom, we have our Wittig reagent. Very good, very good. All right, does that make sense? Any questions about how we got this? Once, twice. Cool, cool. All right. Well, that's the end of chapter 21. Get ready for a whole bunch of nomenclature. Woo! Nomenclature, the most boring part of organic chemistry. But I think it's you guys' favorite, right? Students love nomenclature. All right, so you're about to get a whole bunch of it at once because we're going to see in chapter 22, we're going to be introduced to our acid derivatives a little bit more closely. And we've seen there are several of them, and they're going to require, they're going to have to be named. To first do this, though, we're going to hop back very, very briefly to chapter 19. Chapter 19 is about carboxylic acids. Now, I'm not really going to go over chapter 19 because almost everything in there is kind of redundant and covered in other chapters. So there's not really a unique part of chapter 19 that I have to go over, except for nomenclature of carboxylic acids. So we're briefly going to hop into, oops, sorry, erase my lines, but you can do that. We're going to hop into nomenclature of acids. Oh. All right, so let's see here. Let's look at some rules. All right, you know carboxylic acids, they have the characteristic COOH group, right? C double bond O, and then an OH attached to a carbon or carbon. All right, the first thing that you do is find the longest continuous carbon chain that has your acid group. And you number that chain to give your carboxyl carbon number 1. And it's just like we saw before with aldehydes and ketones, it is understood to be carbon number 1. You don't have to write like a 1 and then a term for the carboxylic acid. You can always assume it's there. All right. Now, how do you actually write this as far as suffixes and everything? It depends. Remember how we did aldehydes where we had like one thing for the acyclic and one thing for the cyclic? We got that again. Why? No idea, because it's stupid. But them's the rules, so we follow them. All right? So here's what you do. You name it as a corresponding alkane. Right? So if your parent chain is 6 carbons, then you name it as like hexane. Except you replace the E with oic acid. And this is for acyclic acids. Okay, so if you had something like this, let's see if we can name it. All right. What's the longest chain with your acid group? 6. Corresponds to hexane, right? But it's not hexane, it's going to be, what's that? Hexanoic acid. So we had hexane, we're going to erase that E and replace it with hexanoic acid. By definition, this is carbon number 1. So that means we go 2, 3, 4, 5, 6. And just like I mentioned before, you don't have to say 1 hexanoic acid. It's assumed. So the numbering really is for your substituents, right? So you have methyl groups at 4 and 5. So that's 4,5 dimethyl hexanoic acid. Okay. So far, so good? Any questions? See if you guys are still writing. I'll stall for a minute or so. You guys finish. And then we'll talk about the cyclic version. And the cyclic one is the one that's stupid. All right. All right. For a cyclic one, again, you're going to name as an alkane. And you're going to leave that alkane name untouched, right? You're not going to take anything off the alkane name. You're going to add the phrase carboxylic acid at the end. And that's for cyclic. All right. So if we had something like this, lots of stuff on this ring. All right, so let's say we had that. That's a cyclic carboxylic acid. All right. So what's the parent name going to be? Cyclohexane. We leave the alkane name untouched. What do we got to do to it? Add carboxylic acid. You know, it's funny, this is all one word too. And then the acid is a separate. Yeah, that is cyclohexane carboxylic acid. Why is it not cyclohexanoic acid, which sounds a lot more efficient to me? I don't know. But that's what IUPAC came up with, so we'll work with it. Just like with acyclics, we're going to assume that this is number one. So you don't have to say one cyclohexane carboxylic acid. And then we're going to number the rest of the ring using, the same guidelines we had in the past. And this will allow us to name our substituents. So it looks like we have a bromo on 5, a methyl on 5, and an ethyl on 2. So we have, let's see. My name's going to look kind of wonky because I'm running out of board space. So you can read at a slant there. So that one is 5 bromo, 2 ethyl, 5 methyl, cyclohexane, carboxylic acid. Whew, that's a mouthful. Any other questions about the IUPAC system for acids? That's basically it. It's pretty simple. However, this is really, really important because the nomenclature system of the rest of our derivatives is going to be dependent on you guys knowing how to do this. That's the IUPAC system. If you look in chapter 19, there's actually a table of a bunch of common names. There actually is a common name system for acids. It's quite archaic though and not used very much anymore, so I'm not going to bother with it. There are 3 particular acids though that go by their common name quite a bit. So I want to highlight those. You have this guy. This is the simplest carboxylic acid. The IUPAC name for this one is methanoic acid, but it's also called formic acid. You guys ever heard of formic acid before? Figured there's a 50-50 chance you might have heard of it. It's pretty common. You ever been bitten by not fire ants, but like black ants and other type of ants that aren't fire ants before? Anybody? No? Say a couple of yeses. What they do is they actually inject you with formic acid and it stings. Fire ants use something else. I forgot what it is, but it's not formic acid. But like you get stung and you get bitten by a little black ant or something, then yeah, they're injecting you with formic acid and it doesn't feel good. All right, then you have this one. That's ethanoic acid, IUPAC name. Much more commonly known by a common name. You guys know this one. Anybody recognize it? It is acetic acid. Very good. Yeah. Good old acetic acid, the vinegar acid. And then you have this one attached to a benzene ring. This is called benzoic acid. And benzoic acid, in fact, is so commonly used that basically its common name has sort of been folded into IUPAC usage as well. Although strictly speaking, the strict IUPAC name for this one would be phenylmethanoic acid. Because you have phenyl hanging off of, well, methanoic acid. Okay? Any questions? One last thing about acids I do want to mention real quick. Sometimes you have more than one acid group on a molecule. Here's an example. To name these, what you do is you name them as an alkane. You got to pick out the chain that has both carboxyl groups in it, right? So like this one, it's a 4-carbon chain. It's got both your groups in it. This one's a little bit different though. What you do is you just leave the alkane name alone. And then you add the suffix dioic acid. So like this one over here, since it's 4 carbons, it's butane, but we add dioic acid to it. So it is butane dioic acid. You're not going to run into too many of these, honestly. And a lot of them actually are more well known by a certain common name. But if you did happen to run into one, that's how you would name it systematically. All right. Any questions about carboxylic acid nomenclature? That is it for carboxylic acid nomenclature. That's it for chapter 19. Don't you wish every chapter was that short? That would be awesome. But it's not. That was just an exception. All right. Now we're going to move on into chapter 22. Chapter 22 is where we have the acid derivatives, right? So we're actually going to see some reactions of acids later on, but we're also going to see reactions of acid derivatives. But first, we're going to get to the nomenclature. All right? So what type of molecule is that? Y'all remember? What do we call it? Carbonyl group of Cl. That is an acid chloride. Yep. So we're going to look at acid chloride nomenclature. All right. Just like with acids, we have a rule for cyclics and a rule for acyclics. This is for acyclic, right? First thing you do is just follow the rules, pretend basically it's a carboxylic acid. Then you change the ic acid to ill chloride. Ic acid to ill chloride. All right, let's take a look at this example. So yeah, like I said, the first thing you do is basically name it as an acid. So you can kind of pretend for the moment that, you know, this Cl is an OH group, right? If this was a carboxylic acid, what would the parent name be? You need to refresh yourself. Look back at the notes we just did for acid nomenclature. Yeah, longest carbon chain with the carboxyl group. Here is 5. That would correspond to pentanoic acid. Right, but it's not an acid. It's an acid chloride, right? So we're going to replace that ic acid with ill chloride. So instead of pentanoic, that's pronounced pentanoil. First time I saw it, you know, I would have said pentanoil, but pentanoil. Doesn't that sound more intelligent and sciencey? Pentanoil. Or you can call it pentanoil. Pentanoyl chloride, right? Just like with acids, you're going to assume that this is carbon number 1. All right, so then you can put in your substituents. We're just going to have an isopropyl group here at number 2, so that becomes 2-isopropyl pentanoyl chloride. Okay. Any questions so far? All ready? All right, so the next one's going to be for cyclic acid chlorides. All right, again, you're going to name as the carboxylic acid. Excuse me, not name as carboxylic acid, you're going to name as an alkane. Sorry. Then you add the phrase carbonyl chloride. So name the parent chain as an alkane, add the words carbonyl chloride. Okay. Let's take a look at this one. Anybody care to venture a guess as to the parent name? Very close. Butane carbonyl chloride, not quite, but very close. Cyclobutane carbonyl chloride. Yeah, since it's a cycle. Yep. Cyclobutane is the name of the parent ring. Then we add carbonyl chloride. All right, this one's going to be carbon number 1. And then we just follow the regular numbering rules. And we have a chloro at number 2, so we just add 2-chloro at the beginning. So that is 2-chloro cyclobutane carbonyl chloride. Okay. That make sense? Any questions? All right. I think we can fit one more in here. All right, let's talk esters. All right, so this is the general structure of an ester, right? Remember, it has a carbonyl group with also an OR group attached to it. All right, now I'm going to take this general structure, I'm going to highlight a couple of different parts. All right, this part over here, that R prime, that's going to be what we call the alkyl portion of your ester. This other part, we're going to call it the acyl portion. Being able to recognize those two parts there will kind of help you as we go through the rules here. All right. The first thing you do whenever you name an ester is you name your alkyl group. And you name it as an alkyl group. So it'll be like methyl, ethyl, propyl, isopropyl, whatever. All right. And then you name your acyl group as carboxylic acid. Except you replace the ic acid part of it with 8. One nice thing about these is that the same rules apply for both cyclic and acyclic esters. So there's not 2 separate sets of guidelines. Okay. Let's take a look at a couple of them. All right, so there's an acyclic ester. All right, what's the first word in our name going to be? Remember, this is a little different than the other one since we have the alkyl and acyl portions. Ethyl, yeah. This R group over here on the other side of the, that's an ethyl group. That's going to be the first part of the name. All right. Then basically what you do, you pretend the acyl group is a carboxylic acid, and then you replace the ic acid with 8. All right, so what would the rest of the name be in this ester for our acyl group? What's that? Close, very close. You forgot one letter, propanoate. Because that would have been propanoic acid. And we replaced the ic acid with, whoops, 8, which I forgot to write. Yeah, ethyl propanoate. Some people will say ethyl propanoate. I say those people are silly. But yeah, whatever. Ethylpropanoate. Now I almost said it too. Ethylpropanoate. Okay. Yeah. Try one more and we're going to be out of time. Just to show you guys it works the same way with cyclics. All right, what's our alkyl group going to be? It's going to be tert-butyl. Yep. So now you got to figure out what to name your acyl group. If that was an acid, what would it be called? So you do have to know the rules for cyclic acids here. Yeah, look back if you need to. If that was an acid, what would it be called? Cyclohexane carboxylic acid. Okay. But again, this is an ester, so just like before, we replace the ic acid with 8, and this becomes tert-butyl cyclohexane carboxylate. All right, we are out of time. In fact, I stole a minute or two from your lives today. I'm so sorry for that. I'll cash it in another time. All right, anything else? Okay, heads up, we will have a quiz on Friday. That will focus on the chapter 20 stuff. So none of this is going to be on the quiz. Chapter 20, very, very reaction heavy. So be familiar with the different reactions that we learned in chapter 20. No, excuse me, chapter 21. My mistake, chapter 21. I forgot which chapter it was. All right, I'll see y'all in lab.